everyone. It's 7:15, we should get started. So, small amount of housekeeping before we start. You probably heard the bad news as you were coming in. Unfortunately, we're not observing tonight. The cloud map is the most ironic cloud map I've ever seen. All of the UK has lovely clear skies, except for this circle of cloud right above Cambridge. So yeah, unfortunately, no stargazing. But it's okay because we have not one or two, but three amazing speakers for you tonight. We've got our two headline speakers, then there'll be some refreshments, and then there's going to be a talk from the Cambridge Astronomical Association all about the New Horizons mission to Pluto. So we've got our two headline speakers though. So Emily and Stephanie are researchers here at the Institute of Astronomy, and they're both going to tell us about different aspects of women in astronomy in honour of the upcoming International Women's Day on the 8th of March. So over to you, Emily.
Yes. Good evening, everyone. My name is Emily Hertig, and I'm a postdoctoral research associate here at the Institute of Astronomy, working on early universe cosmology. And tonight I'm very happy to be here to take you on a journey through space and time, all the way to the very beginning of our universe. And along the way, we'll meet some very important women who made fundamental contributions to our understanding of the universe and our place in the cosmos. So our journey starts here on Earth, looking at a beautiful night sky like this one. There are so many stars, but what do we really know about them? One of the main questions we can ask ourselves is, how far are these stars? We know they're very far away, but how far away are they truly? Well, about a century ago, we really didn't know much about that. We only had one way of measuring the distance to faraway stars, and it was this parallax method. So as you see here, with the movement of the Earth around the Sun, the position of a star can appear to vary slightly. So for example, the angle at which we see that star in June is slightly different from the angle we see it in December. So this only works for stars that are relatively close by, and they appear to move against the background of the fainter stars that are much further away. This was the way we could measure distances to some stars, but only those that were close enough. And here, this is a diagram that's the approximate position of our solar system in one of the arms of our galaxy. And the range within which we could use this method is shown as this yellow circle. It's about 300 light years from ground-based observations. It sounds like a lot, but it's really not. If for comparison, most stars that we can see with the naked eye are contained in this circle. It's about 10,000 light years. So in fact, back in the early 1900s, we didn't know much about this night sky at all. That's until Henrietta Leavitt came along. So she was working in Harvard, and she was employed with this group of women here as a human computer, where they would be looking at data on photographic plates, so images of the sky that were taken, and analyzing patterns, analyzing the variations, the movements, the brightness of stars there. These women were not allowed to use telescopes themselves. They were not allowed to make their own observations. They were really just doing these mechanical data analysis tasks. And as you can see here, they were paid very, very little. Henrietta was receiving $0.3 per hour, which scaled to current times would be about $10 an hour, still really not a lot. So that was a really challenging time for women in science, but she persevered and made a very, very important discovery. So what she was studying on those photographic plates was variable stars. So these are stars whose luminosity, as you can see here, fluctuates in time. They appear to be kind of blinking with a very regular period. And she was looking at groups of these stars that were known to be at about the same distance, and observed a very clear relation between how fast they were fluctuating and how bright those stars were. So the faintest stars were blinking faster, and the brightest stars had much longer periods. And she found out this relation, and it was then quickly used as a new method to measure astronomical distances. So for example, if we have one nearby star that its distance has been measured using the parallax method before, and we can measure its variation period, then we can calibrate it like a candle. You know how bright it is when it's right in front of you. Then when you put it further away, the brightness decreases. So here, for example, we can find a much fainter star that has the same variation period. So they have the same absolute brightness. They're supposed to be as bright as each other, but one is seen much fainter because it's so much further away. And this allowed us to measure distances much, much greater than we could ever have expected. So here's a little visualization of that. That's to remind you, this is a diagram of our own galaxy, the Milky Way. That little yellow circle is what we could measure with parallax methods. That orange circle is the range in which stars that are visible with the naked eye. And within 1 or 2 years of Henrietta's discovery, we were able to measure distances as large as the size of the Milky Way itself. And that was in the 1910s, so 1912 was the discovery. And in the 1920s, this then continued on, and it was revealed that our galaxy is actually not the only one. And that some of those bright, diffuse regions that we could see in the night sky are not actually features of our own galaxy, but are other galaxies of what we call now the local group. For example, this Andromeda is the closest large galaxy. So instead of being just one sort of diffuse region in our own cosmic neighborhood, it is a whole entire galaxy with hundreds of billions of stars that is about 2.5 million light years away. So compared to the initial range of 300 light years for the initial distance measurements, that was a leap forward that really changed our perspective on the universe. Now, having been able to measure distances to other galaxies much more precisely, what followed was the measurement of movement of those galaxies. So are they fixed? Are they moving away from us? Are they getting closer to us? To measure this, we use a method that's inspired by a phenomenon you're probably very familiar with in your everyday life. It's called the Doppler effect. You experience it every day when you walk along the road and an ambulance goes past you. At first, when it's approaching you, you hear the sound becoming more high-pitched. And when it passes you, the sound becomes lower-pitched as the sound waves get stretched. There is a very similar effect for light waves, which is called redshift and blueshift. So if a galaxy is moving closer to us, moving towards us, the light that it's emitted will be shifted slightly towards a bluer color, while if it's moving away from us, we will see what we call a redshift. So Edwin Hubble in 1929 published this very important result where he noticed a very clear correlation between the distance to galaxies within our local group and their recession speed. So this can be summarized as the further a galaxy is, the faster it is moving away from us. And all of them pretty much were moving away from us, not towards us. So that means, as you can see on this little diagram here, that the universe is expanding. If we are here in this red galaxy here at the corner, at first the galaxy that is closest to us, the green one, seems to be moving away a bit slower than the one that's further, the yellow one. So this was the first clear indication that the universe is not fixed and eternal, but that it is evolving, expanding, and that when earlier in its history it must have been smaller, denser, and hotter, and this was what then a few decades later prompted the invention of the Big Bang theory, and that was the first indication that the universe might actually have a beginning and not be eternal. Now, the study of galaxies was really important in the beginning in the entire 20th century, actually, and many features of galaxies were studied. So we've seen their distance, we've seen their recession velocity. Another aspect that was studied intensely was the movement of stars within galaxies. That's as instruments became more and more precise, we're able to measure the speed of individual stars inside other galaxies. And this was the topic of study of Vera Rubin, another very important figure in astronomy. And she attempted to enter Princeton for her graduate studies, but was not allowed because women were not allowed to study there at the time. She then enrolled in Cornell, and she became the first woman to be admitted in the Palomar Observatory, where she was trying to operate the telescope to make her observations. And she was reluctantly let in, with people famously telling her, you can only stay for short periods of time because there is no ladies' bathroom there. So in this famous anecdote, she cut out a little paper skirt, stuck it on the men's drawing of the men's room, said like, well, solved, now you have a ladies' bathroom. So she was quite persistent, and it paid off. So her work on the dynamics of galaxies was very surprising. So what she measured what we call rotation curves. So you see here, galaxies are rotating systems, and this is the effect of gravity, a bit like in the solar system. The planets will rotate around the sun. In a galaxy, we have a movement, a rotational movement of the whole galactic plane of stars around the galactic center. Now, there was a clear expectation from the theory of gravity that we could compute if the entire mass of the galaxy is contained in its visible stars and gas, etc. We would expect the rotation curve to look like this blue curve here. So the center, the stars near the center to be rotating much faster than the ones at the periphery. But Rubin measured that this was not the case at all, in fact. In reality, you see here the red curve. That rotation curve is more or less flat. So that means that the stars at the periphery are rotating almost as fast as the ones near the center, which is impossible if all the mass is accounted for with the matter that we can see. So, in other words, the conclusion from this was that what we see of galaxies, those hundreds of billions of stars, are only a small fraction of what there is in the universe, and that galaxies are in fact embedded in much larger halos of what we call dark matter. And to this day, we still don't know what dark matter is. It is a very important, very active area of research in cosmology, but we know that it makes up the majority of the mass of galaxies. And it makes up a larger portion of the total content of the universe than normal matter does. Still not the majority, though. Many decades later, in the late 1990s, it was found that there is yet another component of the dark sector, which we call dark energy, that drives the accelerated expansion of the universe. That one is about 68%, but that would take a whole other talk to present. So basically, the universe is still very, very mysterious, and the first clear observational evidence for dark matter was the product of a woman astronomer's work. So dark matter is fascinating. Now we know that galaxies are embedded in those halos. Now the question, if we go to larger scales, so not just one galaxy, but a group of galaxies, how does dark matter behave? And this was the topic of study of Margaret Geller, another prominent woman astronomer. She was amongst the first few women to get a PhD in astronomy from Princeton. So as I said before, Vera Rubin could not do that. It was still forbidden. But by the time Margaret Geller came along, she got her PhD in 1975 and was one of the first few. So it's not actually that long ago. And that was one of the first few women to graduate from there in astronomy. And interestingly enough, she also came as a visiting research fellow here at the Institute of Astronomy. So she has been here in Cambridge. So what she discovered, so she basically was working on making a 3D map of a slice of the universe. So measuring the positions of galaxies in the sky and then measuring their distances to make a 3D map. And here we would be at this point there. This would be an angle in the sky, so this would be a 2D slice of that 3D map. And here, this is a measure of distance. So we would be looking at distance of about now 700 million light years on that initial map. So we went from 300 light years to then a few million in the local group. Now we're at 700 million light years. And this revealed a very interesting kind of structure. This revealed that galaxies are not distributed evenly and uniformly across the universe. In fact, they form very large structures of hundreds of millions of light years across, filaments and voids, which we then call the cosmic web, because it looks a bit like a web being weaved through the cosmos. And here we're zooming out. So the first few bits of this were an actual measurements, and now this is more like a simulation, but this basically tells us that dark matter forms filaments and voids. And this finding had a really important implication for what we understand of the very beginning of our universe, because it motivated the leading interpretation now of the first instance after the Big Bang, where we think that the universe went from a quantum regime where it was filled with quantum fields that were randomly fluctuating, and then expanded extremely fast, extremely violently within that tiny, tiny fraction of a second. That's 0 with 31 zeros, 1 seconds. So that's an extremely small amount of time for an expansion of many order of magnitude to happen. But that is what we think connects the quantum world to the macroscopic world, morphing these initial tiny fluctuations, random fluctuations of quantum fields into variations of the density of matter in space, which then, under the influence of gravity, the overdensities would keep attracting more matter, the underdensities would get emptier and emptier, forming exactly this filamentary structure that was discovered by Margaret Geller. So this filamentary structure, this observation of large-scale structures, was one of the main motivations for inflation theory, which is my research area. So what I am now looking at is try to understand what kind of physics possibly can explain such a strange phenomenon, and how do we reconcile the smallest and the largest scales in the universe. And of course, we cannot see all the way to the inflationary epoch. This is not accessible with light. What we can see is the very first light that was ever emitted in the universe, so the first photons that escaped once the universe cooled down enough. And this, which we call, for maybe some of you might have heard, the cosmic microwave background, because it's in the microwave wavelength, same one as in your microwave oven, funnily enough. So this is basically a glow, an afterglow of the Big Bang that's visible all the way across the sky, and we can measure this background radiation, which is the first light ever emitted in the universe, and make a map of it. So this is a projection of the full sky, data from a mission that started in 2013. And you can see here that we see a mostly uniform temperature, but we see small variation of the order of less than 1/1000th of a degree. So this is essentially a map of what the universe looked like 13.7 billion years ago. And we can see variations in its temperature of this order, which is quite amazing, but still much needs to be learned. So there are new instruments being built that just actually finished construction and came online last year. The collaboration I'm a part of is this Simons Observatory. It's a ground-based instrument based in Chile in the Atacama Desert at very high altitude. And it is expected to be 10 times more sensitive than Planck. So this is a really exciting time. We have 1 year almost of data now, and we are already seeing very encouraging results. And the goal of this observatory is to detect direct signatures of inflation and restrict the space of possibilities for what the physical interpretation of this inflationary period is. So basically telling us more about how the universe was born and how fundamental physics behaves at the earliest times and at the highest energies. So this is what my research is about, is optimizing the precision of those images of the very young universe that we get from the Simons Observatory and the meaning of that for fundamental physics. So in summary, we've seen that all of this that we can see on this slice of the universe was unknown about a century ago. We are here at the tip. We didn't know much more than this little point back then, but thanks to contributions from very influential women in astronomy, and of course many others, but I've given you 3 examples here. We are now able to map and study and understand most of this universe all the way up until its very beginning. And the next frontier, the next few years will be really interesting. We have these 2 new experiments. So to map this large-scale structure here, these filaments and voids, we have a new observatory that also just started operations last year, so really an exciting time for cosmology. It will make a much deeper 3D map. So this is actual data that you can see here on this slice. Every point is a galaxy. This is existing data, and we will have much, much more data with this new observatory named after Vera Rubin. And it is the first observatory, first major US astronomy experiment named after a woman. So that's some progress. And thanks to these amazing contributions of these pioneer women who led the way and persevered through really challenging conditions, young scientists like Stephanie and myself now have the chance to be part of wonderfully diverse international collaborations like the Simons Observatory collaboration. We are not yet fully equal. We're still a minority, but it has improved so much. So the science is exciting, and the gender aspect is improving as well. So on this hopeful note, I'll leave you with this stunning image taken with barely 1 year of Rubin Observatory data. Thank you for your attention.
Wonderful. So the good news is this is only the halfway point. While we're doing the changeover, does anyone have any questions for Emily? Yes.
I was just wondering, your talk was fascinating. How can you even conceptualize? How do you think conceptually?
I think.
Hit 13.7. I was like, yeah, I'll check that.
I think at some point it becomes hard to visualize these numbers. I try to use as many animations and these zoom in, zoom out effects that give you kind of an idea of the scales. But to be honest, how big the universe is, how tiny some of these effects are, like inflation, these are orders of magnitude that we're not familiar with. So it's entirely normal to not be able to fully process them intellectually. But that's also one of the reasons that I went into this field, because this just makes me dizzy in the best possible way. It's just fascinating to think about how much bigger the world is than what we see in our daily life. And that's why I research it. Still so much to discover.
Wonderful. I think maybe in the interest of time, should we go to our second talk? I think both, are you happy to be around during the break?
Of course. Yes, I'll be.
Yeah, so any more questions,
Shoot,
please come and talk to both of our speakers in the break. So our second talk is Stephanie Buttigieg, who's going to be telling us all about how Jocelyn Bell detected some of the most interesting objects in the universe. So over to you, Stephanie.
Thank you. Thanks. So through this talk, following from that amazing talk by Emily, hopefully I'll introduce 2 other women that are fundamental in the advancements that we're making in modern astronomy. But first, I just wanted to introduce myself. I'm Stephanie. I'm a 3rd-year PhD student. I was just about to say second, but that ship has sailed. But I'm now a 3rd-year PhD student, unfortunately. I am Maltese, so that picture of me is during a happier time back when I was back home during the summer. But also I'm very passionate about women in science and what we can do to help achieve this gender equality that Emily was talking about. And because of that, I kind of share my experience as a young woman in astronomy, and I join a large, a growing community of these kind of content creators on Instagram, where there's a lot of women sharing their experience. And this is really great because now young girls can see the real life experiences of women in astronomy and what that's like, and and to really see that it's really nothing out of the ordinary. It's just, this is our job. And women are as capable of doing that as men. And so hopefully that will help start changing these ideas that sometimes we might have, that scientists have to fit the specific image. And yeah, we can hopefully improve this gender balance in astronomy. And my research focuses on supermassive black hole mergers. And I really wanted to focus on the work of Jocelyn Bell Burnell, because without her discovery of pulsars, which I'll introduce, I wouldn't really be doing what I'm doing. So let's start from the fundamentals. So what are black holes? So black holes are this region in space-time that was predicted by Einstein's theory of general relativity that says that the force of gravity is just so large that not even light can escape its pull. And these black holes come in two main flavors for us astronomers. So there's the stellar mass or solar mass black holes, and these are the smaller ones. So these, we know how they formed. So at the end of the life of stars, when there's no more fuel to help support the star, it just collapses in under its own gravity and it forms this black hole. And these have masses that are a few times more than that of our sun. But on the other end of the spectrum, we have these supermassive black holes, and as the name suggests, because we're not very creative in this field sometimes, these black holes have masses that can be between 1 million to even 10 billion times the mass of our sun. So these are really huge, and they're really, I like to refer to them as the cosmic giants of our universe. We actually don't quite know how these black holes have formed. If they did form from normal stars, then how did they grow so big? We kind of think that there's a limit to how quickly they can grow. And we also know that they exist very early on in the universe's history, and they're already so big. So how did they get big so quickly? That's still an open question, and I cannot give you an answer to that tonight. So if this video works, yes. So how do we even know that these black holes exist? They're black, right? That's why we call them black holes. And this video shows a set of observations that were made in the 1990s. So this is obviously sped up, but what I want you to focus on is that star in the center, where all of a sudden you can see it go. So what is happening here is that there is a star that's orbiting something, and physicists can use their theory of gravity to try and understand what is causing that star to orbit in that way. And we can work out what the mass of that object in the center should be and in what region it's contained. And the only thing that could explain it is a black hole. We cannot have an object contained in such a small volume. Maybe no, I just wanted to play it again, but I don't know if that will work. We cannot have an object that is contained in such a small volume with such a large mass if it isn't a black hole. So this was the first observation. So what I failed to mention is that this is observations in the center of our very own Milky Way galaxy. So now we call that supermassive black hole Sagittarius A star. And in fact, for those exact observations that I showed you, Andrea Ghez, together with Reinhold Genzel, won the Nobel Prize in Physics for this confirmation of the existence of these supermassive black holes. And she was only one of 5 women that have won the Nobel Prize in Physics over the years. And by the way, the total number of winners is 230. So that is a really poor fraction. I wanted to do a bit of an experiment. Can anyone who can name one other woman Nobel Prize in Physics winner put their hands up? At least one. Marie Curie, yeah. Can you keep it up if you can mention a second person? Ooh, I don't think I can see a single hand, or maybe one. But yeah, so these are the names of the winners. Marie Curie is usually the one that people mention. I also would struggle to mention some of these names, but I do encourage you to go and look them up and research them tonight, because they have done some incredible work in astrophysics. But I think actually only Andrea Ghez is in astrophysics, but in the broader field of physics. Right, so I've just told you that these objects are quite dark and we need to kind of detect them indirectly through the motions of stars that are bright. But actually, now we know that these objects can fuel some of the brightest objects in our universe. And these are called active galactic nuclei. So what happens is that in this region around the black hole, there's such extreme forces of gravity and magnetic forces that you get all of this gas kind of accelerating and heating up, and they shoot these large jets that can escape even even the galaxy itself. And obviously, as you can imagine, these objects are so bright, sometimes they even outshine their host galaxy, and we can see them, and we actually observe them a lot. And through these objects, we can get a really good understanding of the population of supermassive black holes in our universe, because we cannot really see something dark if it's super far away. And when it gets really even more exciting, maybe I'm a bit biased here, is when you have two of these systems. So if you have two galaxies merging together, which, by the way, we know that this is the way that structure grows in our universe, and if both of these galaxies have a central supermassive black hole, which we think most galaxies do, if they merge, you now might be asking the natural question, then do the black holes themselves merge? And this is actually a question that was started to be asked in the Institute of Astronomy. And the answer is yes, they can. So they can form binary systems and can eventually merge with each other and give off large gravitational waves. And so these gravitational waves are ripples in the fabric of space-time that have also been predicted by Einstein's theory of general relativity, which we can potentially detect. But before they do reach that stage where they merge, there's a lot of processes that they have to go through. So they first start in that very first stage, we're in the center of their host galaxies. But once those galaxies merge with each other, there's a lot of interactions that they have to go through with the stars and the gas and the dark matter that Emily talked about to bring them together. And I mean, this is to be expected because when you have two objects that are orbiting around each other, for example, the Earth and the Sun, if the system is not losing energy, then it's in a stable orbit. Thankfully, we're not falling into the Sun. But if there's a process that takes away energy, then it can reduce that distance. This is exactly what these processes do, and we call them hardening mechanisms. Now, unfortunately, if you have two AGNs, so if we're lucky enough that both black holes are powering these bright objects, which is not always guaranteed, then, and if we maybe somehow get them with a good telescope, we can see them in that very first stage. The problem is that when their distance starts to decrease, our resolution becomes poor with the telescope, so we cannot really tell these two objects apart. They just look like one blob to us. So how can we hope to understand these processes? We can, write models for them, but how can we test them against observations if we cannot see these objects? And the answer, again, is gravitational waves. Now, some of you might know that we have detected gravitational waves from merging black holes. So you say, great, now we can go and test them. We have a bit of a problem because we have detected merging black holes, but they're of the lighter kind that I told you about and not of the heavier kind. If we want to go to the really heavy black holes, so the ones that are billions of times the mass of our sun, we need to build gravitational wave detectors that are at the scale of our galaxy. That's obviously impossible. What are you on about? And this is where Jocelyn Bell Burnell comes in to save the day. So Jocelyn Bell Burnell was a PhD student at the University of Cambridge. She was in the Cavendish lab rather than the Institute of Astronomy. And she worked in the Radio Telescope Observatory, which some of you might know. It's only just down the road from the IOA. And she worked with this array of telescopes. Well, this is a telescope. It just kind of looks like poles on the ground. And I was lucky enough to go and actually see it. So it's really not that impressive, but its discoveries were very impressive. So what she noticed when she was looking through her data, she noticed these regular pulses. And in fact, when she saw them, she was like, this is strange. What if, and as a note, I think she wrote LGM on her lab book, which meant little green men, question mark. I think it was an inside joke of like, oh, if you see something you can't explain, oh, just explain it with aliens. But she kept looking at it, and then she went to her supervisor and she said, well, look, I think there's something going on here. And she was dismissed. But she did keep going back. And in fact, what she had discovered was pulsars. So pulsars are what we call neutron stars. So this is when a star is heavy enough and it dies, but it's not quite heavy enough to form a black hole. So instead, it forms this super dense object called a neutron star. And these neutron stars can shoot these jets, radio jets, out from their axis, and they rotate. And when we see, if we're lucky enough that they rotate in the orientation where they kind of sweep over the Earth, we see these pulses. And that's why we call it a pulsar. And what these objects are, they're really, really accurate. So they rotate very, very accurately. There's not a lot of things that can slow them down or speed them up. So we kind of refer to them as cosmic clocks. So this discovery did win the Nobel Prize. Unfortunately, it did not go to Jocelyn. However, Jocelyn Bell Burnell did win a breakthrough prize in physics, and she donated, I believe it was 3 million euros, all for underrepresented groups to study physics. So she did really use this discovery for the greater good. And what we can do with these pulsars is that we can build this galaxy-scale gravitational wave detector. How do we do this? Well, we can find these pulsars in our galaxy. They exist and they're rotating, and we can locate them, and we can observe them for a long time with these radio telescopes, with our normal telescopes. And if we measure a speeding up or a slowing down of these pulsars, and we relate this to each other, so how it's correlated, we say, there's a very unique signature that picks up what we call a gravitational wave background. And in this way, we built this galaxy scale detector. And there was evidence in favor of this gravitational wave background, which is sourced by a population of these merging supermassive black holes all in the background. So rather than picking up just one signal, they're all kind of coming together to have this constant hum that surrounds the Earth. And there was evidence for it in June of 2023, which was the summer right before I started my PhD. And we say evidence because we need to get, so I think it's around 99.5% sure that it's there, but we need to get to like 99.999, something like that. So we just need a little bit more data to confirm it. But thanks to the discovery of Jocelyn, we can now kind of pick up this gravitational wave background. And this is how ChatGPT imagines this gravitational wave background. So you've got the supermassive black holes in the background, and then they kind of create these like ripples next to Earth. But this is how astrophysicists actually look at it. Actually, it's not just one sound, but there's multiple different frequencies that are contributing. So you have the lower ones and then some higher ones. So you can kind of think of this as sound. So you've got those deeper hums and like slightly less deep hums. And all of these kind of frequencies have a different amplitude, or some of them are louder than others. And these are what we observed. So those kind of looking like violins, weird violins, is where we think the amplitude lies for that particular sound. So these are what kind of our observations look like. And to tie it back to my own research and how this relates to the gravitational wave background. So this is the cosmic web that Emily showed you. So here I'm showing you the gas. So where it's bright, there's loads of gas, which indicates that there is loads of galaxies, and where it's dark, there's just nothing really there. It's like a cosmic void. So this is the cosmic web. And this is from the simulation that my supervisor's group, who, by the way, my supervisor is another fantastic woman in science. So this is kind of that cosmic web. And so these simulations, they run on our computers, and they model gas, stars, dark matter, and also black holes. So all of these white spots are where the positions of the black holes are. And in the simulation, they can also merge with each other. And we can use those mergers to predict what the gravitational wave background should look like based on our simulations, which have our best current understanding of physics in them. And this is what my work focuses on. So all those colored lines, I don't want you to focus on exactly what they are, but all those colored lines are models that we can get from these simulations. And they're a prediction to how loud this background is at different frequencies. And if you recognize those slightly neater looking violins now, those are the exact same data that we use, that we get from these pulsars, from the pulsar timing arrays. So now we can really test our models against observations, thanks to the discovery of Jocelyn Bell Burnell, and see if our best models fit the data, which maybe they do, maybe they don't, and that's exactly what my research focuses on. So that was that. I just wanted to say a few words about International Women's Day. This is from last year, but we're running very similar events again this year. We ran, for example, a departmental event where this year we had a little game of like having names of women scientists on sticky notes and playing like a heads-up game, if anyone knows that kind of game. So that was really fun. Last year we ran a quiz. We also have some upcoming school outreach activities. So we get, I think it's around 60 school kids running around the department on 2 days. So the first of those is on Monday. And we run these hands-on workshops highlighting the contribution of women scientists as well. We also have another departmental event coming up where we have one of our great directors, Kathy Clark, giving a talk and talking to us about her career. And last year we also posted some videos, short interviews with women scientists, and also our colleagues kind of talking about how we can support women scientists. So if you want to go and follow the Astronomy Instagram page. And also I promised Matt that I would talk about the open day, which is on the 21st of March, and we will also be there, and we will also be running some fun activities, and we'll be running around the department kind of telling people some cool facts about women astronomers and women scientists in general. So thank you very much for your attention, and happy to take any questions. So that is one of the freaky things that happens with astronomy. You have to really rewire your brain, kind of related to the other question that we've asked, right? That light, when we're in this room, I don't notice the time it takes for that light to travel from the light tube to my eyes. Why? Because it's super quick. So light travels very, very quickly, but it's still finite, right? So it's not immediate that the light arrives to my eye. So when you go on these astronomical distances that our brains just aren't really able to comprehend, light will also take time, and that's what we call light years. So a light year is the distance, it's a distance measure, the distance that light would travel in 1 year. So if you have a planet that's very far away and it lines up exactly with the distance with the time of the dinosaurs, then yeah, theoretically they would point the telescopes at us and they would see dinosaurs walking around on the surface, if they have a really good telescope though.
Sure, yes.
Thanks. Why is the supermassive black holes gravity waves harder to detect compared to the smaller black holes?
Yeah, that's a very good question. So they're not actually harder, but they're just trickier. So gravitational waves also have a frequency. So when we have light, we have a spectrum of light, right? So we have visible light, but we also have infrared, and that has a lower frequency than visible light, right, for example. And in the same way, gravitational waves are also a spectrum. Now, lighter black holes emit gravitational waves at higher frequencies. And for those frequencies, a distance that we can build, I think a few kilometers, so the gravitational wave detectors such as LIGO, they have arms that are a few kilometers long. And that's perfect to detect that exact frequency that they give off. Now, as you get to higher masses, you go to lower frequencies of these gravitational waves, so you need longer arms to be able to detect them. So, for example, another mission that's going up into space is called LISA, the Laser Interferometer Space Antenna, and that will be able, so that has essentially, you're going away from Earth because Earth is limited, but you have longer distances, and that can be able to detect mergers of supermassive black holes that are about 1 million times the mass of our sun. So what these pulsar timing arrays are really good at, then they go to even lower frequencies, which means higher masses. So these are really able to detect those super cool 10 billion time mass solar masses black holes.
Cool. Time for one more maybe?
So you use predictions quite a lot to say, like in 5 years, 1 year, this is is what we predict is going to happen. Do you ever go back 1 year, 5 years ago and go, just how right were we back then?
Yeah. So I think you touched upon a really good point about like kind of the philosophy of astronomy here. So I think astronomy can kind of be split into two. It's not really two separate classes. They do merge together, but you have like the theoretical side and the observational side. So I'm a theoretical astrophysicist, which means that I don't really go into the data and try to clean it up and try to understand the trends that are coming from that data. What I do is I actually go to the physics, go to the theory, go to the simulations, and predict what an observation will look like. So, for example, Einstein, when he was building his theory of general relativity, that theory made a lot of predictions. It made predictions about the existence of a black hole. It made predictions about gravitational waves, but they were all just predictions coming from maths and physics. And then on the other hand, you have these observational astronomers that luckily are there. They can get us data either from gravitational waves or from light, and then we can match those two together. Now, sometimes it doesn't always go prediction and then observation, confirmation. That's the almost ideal. Sometimes you get prediction, observation, ooh, that doesn't look good, drop that prediction, that something must have gone wrong. And sometimes you get observation, what is that? So that's, for example, Jocelyn Bell Burnell's work, right? She looked at something and she was like, I don't know what this is. This is not something that we've predicted. And then you have to go and see what theory you can come up with that matches those predictions. And that's kind of how the field kind of advances together in these kind of steps.
Wonderful. So I think, both the speakers are going to be around in the break. If you want to ask any more questions, can we thank them both again, please? There'll be a short break for refreshments and then back in here for a talk from the CAA all about New Horizons outlook.